The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, a recap of last lecture. We started to talk about liquids. I said I couldn't deal with the liquid using the approach that we have been using for dilute particles, Boltzmann-based equation, for example. And so the discussion on liquid is incomplete and very short. We started on bulk liquids. We said a very useful definition is the measure is the radial distribution function, which actually measures the structure of a liquid itself. And then we introduced the van der Waals equation of states. Historically, it's very important. And of course, we know the ideal gas equation, but the van der Waals equation of states actually give you the liquid and solid states, the vapor and liquid states, and also give you the transition between the liquid to vapor, so vapor dome, at least qualitatively. And then say in terms of treating the transport in liquid, their approach in the past modifying the Boltzmann equation, and this eventually was the, for example, consider rather than Boltzmann equation is a single particle distribution function, two particle distribution function. That was the unschooled approach. But as I mentioned, it was not very successful because you can't really deal with, even with a very complex unschooled equation, which I didn't write down. You cannot deal with liquid. You can deal with approximate treating the denser gas, but it can be extended to liquid. So then we talk about the Einstein's approach. His purpose objective was actually determine the size of molecules, small particles, and he conceived the Brownian motion picture. Although there were experiments, Brownian did experiment long before Einstein, but he didn't seem to realize, and so a lot of his work was gedunking, as he is good at. And he showed the relation between the diffusivity and the viscosity, diffusivity of particles in the fluids and the viscosity of the fluids. And that's an example of the fluctuation, which is diffusion, and dissipation, which is viscosity. It's an example of a fluctuation dissipation theorem. And from the Einstein approach, there was then extension to Langevin equation of motion. So it's essentially F equals to ma, except in the fourth term, there are two terms. One is a random driving force, and the other is a drag force. So when you have particle in a fluid moving, we know that picture is the Stokes drag. But that's actually very general. Its basic drag force is proportional to velocity. And I commented that even the Langevin equation was not quite right the way that's written, because it didn't consider this time, the finite time response when you use the Stokes solution. If you actually write down the time response of the Stokes solution, you actually get an integral differential equation. So you've seen integral equation quite a few times. So that's we'll come back to continue some of this discussion in the last lecture. But then we turn our attention to deal with surfaces and say interface in liquids. And we started with potentials and forces. So what's the most important? In fact, I think somewhere I said before, if you understand energy, you understand momentum, You understand the second entropy, you understand at least, say, all the mechanical work, right? And the F equals, say, the force itself is the gradient of the potential. So we start discussing the force. Particularly, we focused on the Coulombic force, the force interaction due to the charge. We cannot easily deal with the covalent force, right? Where you have to really solve the Schrodinger equation. But for the force interaction due to the charge, direct non-range charge interaction, Coulombic force, you can write starting with the point potential construct. What if you have two positive and negative charge together? That's a dipole. And then you have 1 point charge to a dipole. And you have dipole to dipole. And you can do dipole to semi-infinite object. And finally, we give an expression for example, what's the force, the van der Waals force between, that's the dipole-based model, dipole interaction, between two semi-infinite plates. And the potential is inversely proportional to the separation D between these two surfaces. And this potential is, you can say when you go to smaller d, it goes to more negative. So it's attractive potential. It's an attractive force between the two surfaces. And on the top, the constant here is also called Hamaker constant. And it has its physical origin. If you learn, say, if you do phase change, you'll probably say this has Hamaker constant before. And that's the Casimir force is dipole-dipole. This dipole, the van der Waals force is dipole-dipole interaction. And the extension of that is the Casimir force. And the Casimir force is, as I explained, it was an idea that the force between the two objects, 1 and 2, and can be think about the energy stored in this space between 1 and 2, the medium. That's right. Could be vacuum. And when I think about energy stored, and there is a 0 point, we learned the quantization 1/2 h nu, and then how many modes you have, electromagnetic wave modes in this space. And if each mode contains energy 1/2 h nu, you do that summation of the total energy, and you find out that as the two surfaces get closer to each other, you are excluding modes, so the energy is decreasing, so you have attractive force. So that gives the quantum spin to the van der Waals, say, force interaction picture. And that was the Casimir's very simple paper. If you are interested, you can read it. And then there was an extension by Lifshitz, the Landau Lifshitz book. The Lifshitz is solving this problem from an electrodynamics point of view. Basically, solve the consider the force interaction is, say, due to the 0 point jiggling. So 0 point jiggling means what? There's no temperature there, right? So any object is uncertain. So the position is not fixed. So 0 point has a fluctuation. And this fluctuating will generate electromagnetic wave. The electromagnetic wave propagates to this side. And that will create an interaction between the two sides. So you basically solve Maxwell equation. And then that jiggling is, again, connected to the so-called fluctuation dissipation theorem. So you can calculate the force interaction from electrodynamics perspective. And that's a much more generous theory. So what you have is 1, 2, 3. And what you need is the dielectric constant epsilon1, which could be a function of frequency, and epsilon2, which could be a function of frequency, and epsilon3, which could be a function of frequency. So with that, you can calculate the force interaction in any medium. Sometimes the medium in between are not vacuum, it could be another material, right? And in fact, there is myself even have a little bit confusion here. This concept, again, if you do phase change, you probably encounter. How many of you have heard of disjoining pressure? Anybody has heard about that? Okay, yeah. Disjoining pressure is, again, another concept that encountered in the phase change process. For example, if you consider the evaporation of a liquid film, right? So you have a corner, and the liquid film are spread. And of course, there is a surface tension part, right? But there could be another part, say, very, very thin film spreading much larger distance. And people say that's because of disjoining pressure. And the reason for that is you can think about this as a medium 1. A vacuum is a medium, remember, or say any space for electromagnetic wave is a medium. And the liquid film is medium 3, and whatever the solid is medium 2, right? So I can calculate the 3 medium. Then say, what's the interaction? And it turns out that in some case, right, most of the case, this is attractive. In some cases, the force in between could also be repulsive. Okay? If it's a repulsive force, then there actually will be a stable layer of liquid that sustains on the surface. And that, so that if it's evaporation, if it's a heating, then if you have a liquid film, you help your heat transfer, right? So there is this disjoining pressure that people sometimes use. I think if anyone is interested in understanding this, you should look more into the literature. Okay, so this is the picture that we have in terms of the attractive force. Where we're going is talking about, as I mentioned before, is I have a suspension, I have particles in the liquid, and why the suspension, I can sometimes make this stable, why sometimes I can't make it stable, right? And of course, if it's all attractive, one towards force, then I will not have stability because the particles eventually glue to each other and sediment because of gravity, right? So what I need is a repulsive force. And one, say, common repulsive force, particularly in ionic solution, like say water, is the electrical double layer. So let's spend a little bit of time discuss the electrical double layer. So a lot of solid surfaces, when you immerse in solution, the solid itself, the surface contains charge, right? And you can think about, for example, if I have oxygen termination on the surface, if I put in water, right? What could be happening? You think this will be a hydrophilic, hydrophobic surface? Does it like water or doesn't like water? Huh? It will be hydrophilic most likely, right? Because most likely the surface has oxygen. Oxygen is a negative charge, and water has a hydrogen, and the hydrogen and the oxygen will bond to each other, right? And so a lot of surfaces actually have a lead surface charge, either because of the asymmetry of the bonds, because on the surface atom is different from internal, you don't have the surrounding atom to balance it, or it's just because it just absorbs some ions onto it to have a negative, so a lead charge on the surface. So you have on the solid surface typically, right? Let's say here, I'm drawing the, just inside, I got a net balance of charge on the surface, negative charge. And now if I immersed in a solution that has positive and negative ions, and then you know that the positive ions will go towards the surface just to balance it, right? So what happens is some of this ion will be pretty much glued because the bond is strong enough. So the first molar layer will pretty much like glued onto the surface. And once you are, say, 1 molar away, that force interaction decays rapidly, and the bonding will not be strong enough to hold them. So these other counter ions will move around the surface. But say because of the charge imbalance, so there will be a lot more charge, right, mobile ions in this region in the liquid. So what we will create is in the surface region like a capacitor. On the say solid side, you have one type of charge, ions, and then on the liquid side, you got another type of ions, right? This forms electric double layer, and in fact, if you define more carefully, and the immobile layer of ions is a Stern layer. It's called Stern. Yes. Okay. And then the mobile layer between this Stern layer and the outside, where eventually they will go, the charge will go to neutrality, the bulk region of the fluids where it's not influenced by the surface, right? So this layer is the double layer. If you do electrochemical devices, if you do supercapacitors, for example, where capacitance is proportional. If you think about capacitors, capacitance is proportional to area, right? And it's inversely proportional to distance and the dielectric constant, right? So supercapacitor is the one that you create a large surface area by making nanoporous materials, and then you put in the electrolyte, because how you can create that capacitance layer, you create the electrolyte and put it into there, and you hope that the capacitance, the local capacitance between the electrolyte and solid, and using that to form your total capacitance of a supercapacitor, right? And in supercapacitor, this layer is very important, not just the electric double layer. And if you do electrokinetics, right? If you electrokinetics including electroosmosis and where the particle moves, or when you apply electric field, or say the liquid mode in the electrokinetics is when, so both are because either the particle is charged, the solid is charged, or the other case is the liquid is charged, right? So this in those cases, the electric double layer very important. And so first, the density of the ion on the surface. So density of ion on surface. And this one can be related to the case when you have zero charge on the surface, right? So one case you don't have any charge on the surface. What's the density? So this is the 0 point charge density. And then we have, because I have certain ions absorbed on the surface, right? I have then, say, a surface potential and divided by kBT. So this is essentially the Boltzmann statistics, Boltzmann distribution, right? If you recall the Boltzmann distribution, what we have is the energy over kBt, right? The probability of certain particles having certain energy. And this energy is related to electrostatic potential psi by the charge Q, right? Normalized to charge. And Q is if I have an atom that has a certain number of, for example, protons, Z, right? And then Z times E gives me the charge. E is the charge per electron. So Q is ZE. That's why I have ZE times electrostatic potential, which is surface potential, divided by kBt. OK, and this gives me a way to actually define the surface potential as a log, and you can inverse that. Now, what I would like to find is what's the potential, electrostatic potential distribution in the double layer. Okay? So because I have a surface potential cosine from the surface, on the surface, right? And then when I move away from the surface, there will be a distribution because the potential eventually will disappear. And I want to say how thick is this layer, is the electric double layer. So from the solving the distribution. So the way I do it is they look into the Poisson equation, which is one of the 4 Maxwell equations, right? So what we had in the Maxwell equation is the displacement divergence equals the net charge per unit volume at local charge density. That's what we had before. And D will be, let me write the 1D form. I don't want to do too complicated. So I will write epsilon, right? Or epsilon 0, epsilon r. This is the epsilon r is relative dielectric constant. Epsilon 0 is dielectric constant vacuum. Together give me the epsilon. And so this will be times the electric field, right? Because D equals epsilon times E, electric field. And so electric field, I use, you should write a larger epsilon. I'm running out of symbols. And dx equals rho, right? And electric field is the gradient of the electrostatic potential, negative gradient, right? So I have really epsilon r, the negative gradient of electrostatic potential dx squared. So that's on the left-hand side of the Poisson equation, right? On the right-hand side, I need to write my charge. So recall here is my solid, and locally I have electrostatic potential, right? And given electrostatic potential, I know the energy is Q. In fact, this is reverse. Sorry. This is the psi equals the energy times Q, right? So energy, local energy is, electrostatic energy is a Q times psi, right? And then local Boltzmann statistical distribution for that species can be written as the, let's say, is I have a Zi, different species in the solution, Zi, E. So this is for species I, and per ion, and the density of the ion, 0 means semi-infinite way. And now, because locally I have a potential difference from the semi-infinite, so I have Zi E psi, that's the energy divided by kBt. So this is the Boltzmann distribution. Boltzmann distribution, how many particles? Each particle carries this much charge. And I sum up with all the species in the ion, right? And here I got the so-called Poisson-Boltzmann equation. Okay, here we have Poisson. I don't want to write the Poisson. How to write Poisson? 2S, P-O. Okay. So, Boltzmann. Right? So solving this Poisson-Boltzmann equation, you should be able to obtain the local field, electrostatic field distribution in the double layer. And it turns out this is not so easy to solve. In fact, you could solve this problem more rigorously. And the first one was an approximate solution. And this first approximation was by Debye. It's called the Debye-Hu solution theory. Okay, Debye-Hu theory. And it's linearized. So rather than using the exponential, we will assume that exponential can be linearized. And this happens when the exponent is small. So when the potential is not large, ZIE psi much less than KBT. And remember, KBT is of the order, KBT is 26 millielectron volts at room temperature. So this, in fact, is a poor approximation. And in most cases, the surface potential will be larger. In many cases that I know is larger than this value. So it's not a very good one, but it gives it's very instructive. Because of this, I can actually linearize it. So epsilon r, epsilon d psi, dx squared, and equals to I. So zi e n0 I linearize. So I get 1 mass ZIE psi and KBT. Right? And infinite away from the double layer, I have a balance of negative and positive charge. So that's neutrality. So I have positive and negative. This of the first term is actually 0. Right? So what I have then on the left-hand side, if the first term is 0, I can pull out the psi. I have I ZI square, E square, and KBT, and N0I. So now I actually get a simple second-order differential equation for the potential distribution near the surface here. Right? It's an exponential decay function. As you can see, it's a second order. This is your constant. If I divide the epsilon 0, epsilon r to this side, this is a constant for that exponential decay. So what I have then, the potential. And what I really want to say, this potential I should use, because I'm dealing with the double layer, I should not actually use psi s. I should use the potential at this point. Let's say S0. That's where I start looking into the decay, the diffuse layer here. So what I have here is psi S0 exponential minus x over delta. And this delta, the inverse of this delta is just the square root of what I've written here. So the square root of I, zi square, e square, and n0I, and epsilon 0, epsilon r, kbt. So this delta itself, delta is called the Debye length. And you go to look at the literature in semiconductor p-n junction, the space charge region is the same expression. In fact, when you solve for the potential of a p-n junction, you solve the same Poisson-Boltzmann equation, and you use this linearization, you get a similar expression, and that is also called the Debye length in p-n junction. And the history is the electrochemical battery cells was long developed between the p-n junction, right? So you can see the solid-state devices actually use this concept that was developed for the electrochemical in electrochemistry. Okay, so it will be interesting to see what does this mean. How thick is this Debye length, right? If I have water, I put some salt into it. What's my Debye length? I should be able to estimate given the expression here. Let's take one example. I'm going to put one grain of salt, sodium chloride, and into water. And put in 1 liter water. 1 cubic meter, 1 liter of water, right? And what I need to find out what's the solution infinite way, what's the equilibrium concentration of the ions. You see concentration of the ions and just dielectric constant, say dielectric constant, right? And this is the inverse. So 1 cubic liter, millimeter, and the density of salt is 2.5. So the density is 2.5 gram per cubic centimeter. So with this, I will get what I have here is 10 to the minus 3. So here is 10 to the minus 3 cubic centimeter times 2.5 gram per centimeter. And I have here what I have here. This is centimeters. No, this is centimeter. And I have 2.5 milligram, right, of salt. And then how much is that in terms of mole? So I realize my notes has a 10 to the minus 3 order of magnitude difference. I forgot this. So say the in terms of mole is 2.5 10 to the minus 3 gram, right? And the molar mass of sodium chloride, sodium is 11, chloride is 17. So total is 28 times the multiple factor of 2. That's my molar mass. So here I have is 56 gram per mole. And this will give me 0.045 10 to the minus 3 mole. Huh? Okay, so this is my mole number. And then I also know one more. I have Avogadro constant. So I have how many ions inside, right? So what I have here, I multiply Avogadro constant, Na, which is 6 10 to the minus positive 23 ions per mole. So I have this number of ions, 23. So I will get this equals the, okay, so the Lambert density is per liter, right? So 0.045 10 to the minus 3 times 6 10 to 23. That's the number of ions per liter is 10 to the minus 3 cubic meter. And so this cancel. And what I'll have is 0.27 10 to the 23 per cubic meter. That's the K number I need, right? So if you go to do this, I think my length here, because this one, what I have, delta, because the dielectric constant of water is about 80, right? Water is a very large dielectric constant. If you go to a polar liquid, right, then the dielectric constant will be much smaller. And because of that, it's actually much harder to put an ion into a polar liquid. So it's water, you can dissolve ion much easier because of the large dielectric constant. But anyway, so if you do that, what I have here, originally 1.5, but here, because I realized I missed this, so it should be 10 to the third nanometer. You can go to check. So this will give me 15 to 20 nanometer, tenths of a nanometer. Yes?
So for Z, do you use the full nuclear charge or the screwed nuclear charge?
I use just the valence here. So I should use the screened. I use screened. Wait a second. So what should I use? Z. If I think about it, Z. Yeah, it should use screened because it's a lead charge. You have most of the ion, the electrons is glued onto the nucleus. I should use the charge of the mobile, lead charge of the mobile ions. Okay, so the point is, you can say the typical Debye length is of the order, depends on how much salt you put there, of the order of 10 nanometers, right? You put more salt, your Debye length will be smaller, and you put less salt, your Debye length will be longer. So this is the influence of the electric double layer, how far away they extend in the liquid. And now, once I have that, then the next question is, this is around a single surface, and what's the pressure, right? And what's the force between two surfaces? So to understand that, I can think about first, if I have a double layer, with this you can also use this as the effective thickness for capacitor, right? The capacitor is a positive negative charge, and that's your effective thickness. And the good thing is that with capacitor, the difference between electric double layer and p-n junction is that there really is no charge. Ions cannot get into the solid, right? P-n junction, you have electrons, you have holes, they can recombine. So you seldom use a p-n junction, simple p-n junction to store charge, but you can use the electrical double layer to store charge for the supercapacitors, right? And once the ions get into the solid, it becomes a chemical reaction. That's your battery there. Your battery actually is the ion gets into the electrode, right? So what we have here, let's look at the pressure. So I have, for example, I have negative ion on the surface. I have counter ion positive, and they will attract each other, right? So I have attractive force. And if I have force, unless I have counter force, otherwise all those ions should go to the plate, right? They will move. So I got to have a counter force. The counter force is the pressure I have generated in the double layer. So I have a pressure. I can think this is a P. This is a Px plus dx. And this is a dx, right? So the balance of this pressure force is against the electrostatic force. So I write the force balance. And the force balance will tell me this is a dp dx, and negative and plus the density of the charge times the electric field on the charge is d psi dx, and this should balance it. Right? So this is the force balance, and of course now I have the solution for the, in fact, you can use the original Poisson-Boltzmann, say Poisson-Boltzmann equation. You can write this as dp equals minus d psi, because you can integrate dx directly, get rid of it, and the charge density is I ZIE N0I exponential minus epsilon, ZIE psi and kBt. So in this case, I do not, this is just the charge density I've written in the right-hand side of Poisson-Boltzmann equation. I can integrate without any approximation in this case. And if you do an integration, I get a p at the x minus p at the infinite. I integrate to infinite, an infinite way. This is the concentration is n0I, so I will have sigma I and kBt and nix minus n0I. So if you look at this, and you can think this as this is negative, so I have positive ions here trapped, and I have more positive ions than infinite way. So this term is positive. So what it means is the pressure is positive, is higher in the double layer than higher than the pressure away from the double layer. Okay. And now when I have two surfaces, because I want to look at, right, I have direct force interaction, that's a van der Waals force or Casimir force interaction between the two surfaces. That's what we discussed before. And now because the pressure in the double layer is positive, so when I bring the two surfaces very close, the pressure is positive inside, it will repulse the two surfaces. So I have a repulsion force that could balance the attraction force, right? So this is the repulsive force due to the electric double layer. Now, with that, I can now start thinking about when I put particles into liquid when they are stable, because I have attractive van der Waals force, and I have also repulsive electrostatic, the double layer force here. So I have, in terms of the separation of the two particles, right, in the liquid, when they are getting closer, that's van der Waals force, right? And when they are getting closer together, the pressure in between the liquid due to the electric double layer increases, and that's a repulsive. So this is the potential from the force to potential, and you superimpose the two, and you say which one wins. And if the van der Waals force is very strong, you will be just attract to each other. And so what do you want? So if I do the superposition of the two forces, you could have different scenarios. And one scenario is like this, right? And here is the van der Waals force, and then the repulsive potential due to the electrostatic. When I get in really close, this van der Waals force wins again, so you start to attract each other. And now if you look at the situation, the particle tends to stay to minimum, right? Minimum energy point. And there are different scenarios. One minimum is here, and the absolute minimum is here, right? And this minimum, if the potential barrier here is much larger than the kT, then you actually have a quasi-stable. Colloid is quasi-stable, right? It can stay this way, keep a distance between the particles, and until somehow you force them much closer, right? So this is the different scenario you can have that will push the particle away, and or you could have this, the one where it's just for wins, right? And in this case, you never get a stability. I wasn't sure whether in this case you can get stability, because this time I'm considering only two particles, maybe it all push to the boundaries of the container, right? And so this one is the real, say, metastable state. And that's when you want to use the electrostatic method to stabilize the colloids. And in that case, you know, right, if you want to destabilize it, you add a drop of salt, it will just fall to the bottom. You change your electrostatic potential. And there are different ways. There are other ways. This is when you deal with the ionic solution, it's much easier. And when you deal with a nonpolar solution where you cannot adjust the ions concentration in the solution, it's much more difficult. And in that case, what you do is you, for example, wrap the surface of the particle with polymers, and then you use the configurational repulsion. And say people call different. There are different forces in this case to stabilize the solution. So using this is a surfactant way to stabilize. And in fact, I was thinking even this morning whether the surfactant, I haven't checked. I have to say I haven't checked the literature. People use entropic energy or that to explain it. I was just thinking whether one could still go to modify the Lifshitz theory, and somehow whether this polymer can introduce repulsion, just like we say you can have a repulsive force if the dielectric constant of the mediums are different. But I wasn't sure. I acknowledge I didn't check literature. Okay, so that's the basics with the electric double layer. And if you do microfluidics or nanofluidics, you know that people have used the electric double layer when you deal with the liquid. This is where there are a lot of technology advances in the past. And people using the electric double layer to make devices. And one of this well-established is this is long before micro nanotechnology. Okay, that's the electroosmosis, right? And or electrophoretics. First, electrophoretic. And the phoretic is always some particle is moving, solid is moving. And when we have electrophoretic, what I mean is I have particles. I put it in a liquid, ionic liquid, and the particle will, of course, have absorbed the ions, right? And then say the surrounding has counter ions, and effectively, when I apply an electric field on the particle, they will move depends on the lead imbalance, right? So effectively, this particle is like a charged particle, and I give an electric field, the particle will move, right? And of course, the motion is a balance of the driving force, which is the electrostatic force, the charge times electric field, balance the drag force, which is a typical small particle. You can use the Stokes expression, right? So if I do apply an electric field, and in fact, you can say, depends on whether it's a positive or negative charge, it can go different directions, right? Surface charge. So with that, you can tell whether your surface of the solid is charged positively or negatively. And even though, say, there's surrounding charge moving within the liquid, but there's a lead charge difference, right? So I have then, say, I do the balance is 3 pi mu d times the velocity. That's the Stokes force. And then I have the charge on the surface, Q times the electric field. And this gives me the velocity. I can easily Q times electric field apply, and 3 pi mu d. Right? You use this to, for example, you can measure the velocity of the particle moving. You can use that to do your particle sizing. Or you can also use that. So say most of the time people actually use this to determine the Q on the surface. Right? And the Q is, this one is not the surface potential because it's a lead surface, right? Because it has, if the particle is negative charge, there's surrounding also positive charge that adhere to the surface, and there are some shear, there's some mobile charges still moving with it. So effectively, you are really is looking at the lead charge in a certain sphere that effectively is moving with the solid, right? And this potential, you can go to say, what's the effective potential? That's your zeta potential. That's zeta potential is this Q and 2 pi epsilon 0 epsilon r, and approximately is the thickness of the Debye layer, and the d is diameter over 2. So when this is much larger than the diameter, you can say that the measuring zeta potential is effective, is measuring the number of charge. Okay, so this is the electrophoretic flow, where you use the field to drive the particle motion, and people you can actually buy commercial equipment that's for example, that measure the zeta potential pretty much based on this principle. And the other situation is, let's suppose you want to use the electric field to drive a fluid flow in the channel, right? And if you have solid, you have a liquid inside, and you have, in this case, if you apply a voltage, electric field in the flow in the actual direction, and now what happens is, of course, you have fixed ions that do not move. You have then double layer ions that's mobile. And those double layer, of course, is only near the surface, right? So if we apply an electric field, this double layer will move, let's suppose these are the positive charge double layer, and they will move towards the field direction. And because they are moving, they will drag the surrounding fluids to move. So what you have is essentially, actually, because now it's almost like you have a sleep boundary condition. You do have that very thin layer between this thin layer and the some immobile ions. That's very thin, few nanometers, for example. And the rest is all moving. So it's like a plug flow where the velocity distribution through the whole channel is uniform, right? So you draw it, it's pretty much a plug flow situation, except they're really close to the surface. And so, of course, then you have to balance your viscous. And this is how people use, for example, electro-osmotic pump. Right? This is osmotic, electro-osmotic. Okay. And you can show that the velocity here, of this motion is epsilon 0, epsilon r, and they apply electric field and viscosity, and they again the zeta potential. Okay, so that's the electrokinetics, including Phoretic, osmotic, and that due to the electric double layer. And what we're moving on next is talking about surface tension and phase change. Okay, surface tension, and so what is the surface tension? First question is, what's the unit of surface tension? Newton per meter. Okay. So let's look at, understand a little bit more on surface tension. And surface tension is the energy. So first is the unit is Newton per meter. Right? You think of it typically as a force, right? Surface tension as a force. But then I can write this Newton times meter per meter square. That's joule per meter square. What is it? It's a surface energy, right? So the surface tension is how much energy I need to create a surface. Okay? And we can start with the same material. So if I have material 1, right? I want to break it. What's the minimum energy I need to break this surface, right? The minimum energy I need is once I break into 2 halves, I got exposed to a surface there, right? So the surface energy is then, the surface energy, gamma 1, is then the work, half of the work I need to do, minimal work I need to do to create these 2 fresh surfaces, right? So that's the cohesive energy. It's the same material. How much energy you need? It's a cohesive energy, right? Cohesion. And W here is the work of cohesion. And so this is a 1 case. Now, if I have 2 different materials, 1 and 2, how much energy I need to break and create 2 different surfaces, right? Material 1 and material 2. Okay. And this is the interface between 2 different materials. That's my surface tension between the 2 materials. So from an energy perspective, it's much easier to understand. And my surface tension right? So surface tension exists for any surface, not only liquid, but also solid. In the surface tension, in this case, R12 can be expressed in terms of the surface energy R1 plus R2 and minus 2 times R. So here I only look at the van der Waals part. So van der Waals part of this how much van der Waals surface energy for if I break up surface 1 only and break up surface 2 only. Okay, so this gives us some ways to estimate the surface energy and surface tension. Now you go back to what we dealt with before, right? I can think about really when I bring 2 surfaces together, what's the, here we discuss what's the van der Waals force, what's the van der Waals potential between the two surfaces, right? So with these basics, you can actually do your sort of back of envelope calculation in terms of how strong is the bonding between two surfaces. And of course, for this part, there is a covalent part, right? If the two surfaces are covalently bonded, I just can't deal with easily, right? I told you how to calculate van der Waals, the dipole-dipole interaction, and charge-dipole interaction, but I can't do easily the covalent bonds. That requires more sophisticated calculation based on, for example, quantum mechanics. Schrodinger equation solution. Okay, so with this basic understanding, you can, of course, you all heard about, let's say, this Laplace equation. And so we have Laplace equation. If I have a sphere, simplest case is a sphere, right? And then I have the difference in the local radius curvature. I have the pressure difference, which you can say as say P inside, outside, and is a 2 gamma over R. R is the radius of the sphere, right? So that's the gamma is the surface tension or surface energy. That's the Laplace equation. The Young equation is when you have a droplet on the different surface where you have whether the surface, the droplet was spread or not. So the contact angle of this is really energy balance. Or you can think of this, it's easier in this case to do a force balance. I have medium 3, medium 1, and medium 2, the contact angle theta. So you do your force balance, you will say this is a R23, gamma 23. And here gamma 13 and gamma 12. So I have gamma 13 equals gamma 23 cosine theta plus gamma 12. And this is the Young equation. So now, sometimes we call this Laplace-Young equation. Okay. So this is you know this, I'm sure, and you have seen in different situations. And what I'm going to discuss next is the size effect on phase transition. Okay, and with this basic understanding on the surface tension, let's look at the size effects on phase transition. Right. So if I have a droplet or a vapor bubble, it turns out that the thermodynamic properties of this droplet or bubble are very different from bulk materials. And this is based on if I have, or this also apply when I have a liquid, say a solid nanoparticle, and the melting, this could all happen, right? So basically, I'm looking at the equilibrium thermodynamics of a particle with the surrounding. And this particle could be a liquid droplet or a vapor. And when I look at the equilibrium, right? So I'm looking at the mass equilibrium. What's the condition for mass equilibrium? Right? What's the condition? Mass transfer. Huh? You all forget? Huh?
Potential gradient is 0.
So the chemical potential gradient, the chemical potential on both sides equal each other, right? The equilibrium, you have mechanical is pressure, heat is temperature, mass is chemical potential. Can't forget that. Okay. So what I have is the chemical potential equal each other. That's always my condition. And the chemical potential turns out in the differential form for each phase, right? This is where you can see the Gibbs free energy is the enthalpy minus Ts, right? And for each phase, the Gibbs free energy is mu times n times mu, number of particles times the chemical potential. And with these two together, you can prove the Gibbs-Duhem equation, which says where I have S dt minus V, the specific volume dP plus d mu equals 0. Okay, that's the starting point to derive all the Lex expressions. Is Gibbs-Duhem relation plus the pressure, where because when I have two phases, this applies to each phase. When two phases at equilibrium, d mu difference between the two are 0, because the mu prime mu equals to mu double prime. So let's look at the case where, of course, I have the pressure difference, dP prime minus P, 1 double prime minus P prime equals to d 2 gamma over r, right? That's the Laplace equation. And now I consider, first I consider the phase change, which happens also under constant temperature, right? Temperature doesn't change in the phase change process. And at the equilibrium, the two chemical potential must be the same. So what I have here, this doesn't change, this doesn't change, and what I need to have is then the two phases V dP, V prime, dP prime equals V double prime, dP double prime, right? Specific volume times the pressure, that's equal to each other to balance, to have the equilibrium condition so that the chemical potential on both sides. And with the two, I can replace, say, the pressure, say one of this. I can replace, for example, specific volume. But I need to say which one is vapor phase, because I don't know the, say in the vapor phase, I use the ideal gas law. So if I have first as a droplet, I keep my P double prime. And so let me say if I have, first I have a droplet. If it's a droplet, right? And it's say, so we in the vapor phase, I have V prime equals RT and P prime, right? So that's in the vapor phase here, V prime equals, so I can replace with P prime, and then I can put a P double prime in terms of P prime. So I can eliminate to have an equation to solve for dP prime only. And if you solve for that, so combined with the equation we have, you'll find out that P prime equals P0 exponential and 2 gamma over R and V double prime RT. V double prime is the liquid, the specific volume during the of the liquid doesn't change, right? Doesn't change much. So I can keep that as a constant when I do the integration. And this shows that if I have a droplet, liquid droplet, right, and small droplet, the corresponding outside vapor pressure is higher, right? So what does that mean? If I have a cloud of droplets a different size at one temperature, what happens to the small droplet?
Grows faster.
The small droplet will evaporate faster because the vapor pressure is higher, so they will disappear. So it's the bigger particle win, right? And if you do solid, for example, that's called Oswald ripening. Your nanoparticle together, bigger nanoparticle will eat small nanoparticles. And if you do liquid, that's the same. Say the small small droplets disappear faster. Okay. And now, if I do a bubble, you do the same, right? You reverse it, right? In this case, your bubble is inside, so P double prime is, say, nRT, and then you solve your equation. Again, what I have is P double prime equals P0 exponential minus 2 gamma R V prime. Outside is liquid, so V prime is constant, RT. So pressure will be lower. The vapor pressure of the bubble is lower. What does that mean? For example, this is where people want to use capillary condensation. You have nano channels or micron channels, right? The liquid will condense into the channel. And in the condensation, let's suppose this is a vapor, V prime, and say liquid is here, right? Now I have a half bubble, right? It's the same scenario. And in this case, oh, I'm sorry, this is a double prime, this is a V prime, right? That's my inside is double prime. This is the inside, the curvature here is double prime, right? So what it says, in this curvature region, the vapor pressure is lower than bulk. And what it means is if I have a vapor here at a certain temperature, I can still have condensation inside at that temperature. Okay? And that's a capillary condensation. And this will happen until you fill to the top, and eventually at the top your curvature disappear. You don't have condensation anymore. Okay. And you can do further same analysis. You can, so here we're doing the say vapor pressure analysis. You can even do the temperature analysis, right? So if I have a nanoparticle, and here I can write that during the phase change process, delta S is delta H over T. That's a phase change temperature, right? So you can, again, go back to the phase change process, analyze what will be the trend of my temperature change of particles. And you will find out if I have a small particle, the delta H T0 minus T equals, here is R log 2 gamma R plus P prime over P prime. So what happens is, what this tells me, if I have a small droplet, the melting temperature compared to a flat surface melting temperature will be lower. Okay? And this has been even proven in solid, where there are experiments, if you make a silver nanoparticles, and you put there, the temperature could be as low as the melting temperature of a few, let's say just 100 or 200 degrees. So people try to use this effect to print the nanoparticle and make printable circuit, and you can put on plastic, and you fire up to a very low temperature, they will solidify the groove. And in fact, say once I was thinking about this, I didn't fire pattern, but then somebody else did it. And people think about using the interface, right? And if you think about solder is a lower temperature, but say it's typically made of alloys, and alloy has a little bit worse thermal conductivity. But if I just use silver nanoparticle with low temperature, I can still fire the 100, 200 degree, and they will grow big, but it's permanent. That's once they grow big, they have higher thermal conductivity. So that was, random. I used to have an entropy generation table. That's one of the idea generated. Didn't fire pattern. Somebody did it, fire pattern. So you can explore those kind of different effects. And those are all classical. All those relations were derived by Kelvin. Okay? Kelvin wrote over 500 papers. Okay. Poisson only wrote 27 papers, Poisson. So you don't have to write many papers to leave your name behind. Okay. There are people write a lot. Every paper is important. And the final comment is even surface tension can depend on the size. Okay. So there are also theory on the surface tension, size dependent on surface tension, and this were discussed in the book. And with that, I sort of close this discussion on liquid. And the last lecture, what I'm going to do, I'm surprised that I can actually go to chapter 10. Many times I stop chapter 7, so you have been enduring with me, moving very fast. But I'll talk about more on the linear response theory, molecular dynamic simulation.